Welcome back to another episode of Game Theory. Today we are still in Chapter 12, looking at evolutionary games. So last time we looked at when you have one species but two different types. Now we're going to look at when you have two different species and two types within each species. Now your book also goes into when you have three types, but that gets substantially more complicated. I think that would take us too far astray. So I'm going to stick to when there's either two types or when there are two species. So let's say species 1 can be either A types or B types, named rather unimaginatively. And species 2, you're either an X type or a Y type. Any species interact and the fitness levels depends upon how much of the other species is present. Like you'd imagine, the fitness level of cats depends upon, in part, what kind of mice are out there. And likewise, the fitness of the mice depends upon what kinds of cats are out there. So let's say the fitness levels are as follows. And we'll have PA be the fraction of A types. So that means that 1 minus PA are B types. And it also means that we'll also have PX be the fraction of X types and 1 minus PX be fraction of Y types. So we'll take the same process as we had before, but now the stability analysis will be more complicated. Hang on just a moment while I replace my pencil. There we go. So first we want to find when is each type equally fit. Now it's going to be a little more complicated here because we have two types for each species, so we got to do a bit more work. So remember the equilibria is going to be similar to what we had before. So equilibria can be everybody's the same type, or for each species. So it could be like all A types and all X types, or all A types, all Y types, etc. And there's also the monomorphism. There's also the polymorphism where some are A types, some are B types, and also some are X types, some are Y types. So we gotta find what is that polymorphism, analogous to the mixed strategy Nash equilibria. So let's find the expected fitness of the A types. With probability Px, they meet an X type, and they get a fitness level of 3. With probability 1 minus Px, we meet a Y type. In that case, our fitness level is 0. Now I'll find the expected fitness of the B types. With probability px, they meet an x type and they get a fitness level of 0. And now with probability 1 minus px, they meet a y type and get a fitness level of 1. Let's simplify. So that just goes away. 0 times 1 minus px is 0, so we're left with 3px. For this one down here, that goes away. We're left with 1 minus px. So we had just one species to be done here with step 1, but here we have 2 species. We also have to find out when are the x types and y types equally fit. So if you're an x type, then with probability PA, you meet an A type and you get a fitness level of 1. With probability 1 minus PA, though, you meet a B type. In that case, you get 0. Now, if you're a Y type, that's probability PA, you meet an A type. In that case, you're getting nothing. With probability 1 minus PA, you meet a B type. In that case, you get 3. So let's simplify. This 0 is going to knock out that. We're left with just PA. Here the 0 is going to knock out that term. Distribute 3 through, and we get 3 minus 3 PA. I guess I should relabel my step here. Step 1 is you find the expected fitness of each type. All right, so now we're done with step 1. We found for each type of each species the expected fitness levels. The next step is going to be we find when each type is equally fit. So it should have been step 2 I originally had written. So again, we already know what some of the equilibria look like. There's an equilibria with all A types, all X types, all B types, all X types, etc. But there's also that mixed equilibria, the polymorphism, that they find as well. So we gotta find when is E of FA equal to E of FB. So when are the A types and B types equally fit? So the fitness of the A types is 3 times px. The fitness of the B types is 1 minus px. So we gotta go and solve that. So let's add a px to both sides. 4px equals 1. Then we divide both sides by 4, and we get that px is 1 over 4. Now, this is not a mistake. The fitness of the A and B types depends upon not the fraction of A and B types, but rather the fraction of X and Y types. That's because the species is interacting with the other species. It's like my example earlier where the fitness of the mice depends upon what kinds of cats there are. So the fraction of a certain kind of cat is going to determine the fitness of each type of mouse. So now we're going to do the same thing for the X and Y types. We have to find whereas one of the X and Y types equally fit. So we said that the X types have fitness of PA. The Y types have fitness 3 minus 3PA. So let's go and rearrange that. Let's add 3PA to both sides. This will become a 4PA. Then we have just 3 over there. Divide both sides by 4, and what we're going to be left with is that PA is 3 over 4. So the same principle applies here as well. The fitness of the X and Y types depends upon the fraction of A and B types, the other species. So that wraps up step 2. We know each type of each species is equally fit. The last step is to draw the graphs and analyze stability. The graphical analysis for these two species games is substantially more complicated. So let me show you how that's going to work. So the first thing we're going to do is draw the graphs for each type and each species separately. Then we're going to put it all together to look at the stability overall. So let's start by looking at the fitness for the let's start with the A and B types. So we put the fitness on the y-axis. Now the fitness of the A and B types again depends upon not the fraction of A and B's, but rather the fraction of x's and y's. This is going to be px over here. That's not a mistake. So we said back here that the fitness of the A types was 3px. That means our intercept is going to be 0, and our slope is going to be 3. So label that FA. For the B types, the fitness level was 1 minus px. So intercept is 1, slope is -1. And we established that they are going to be equally fit when px is 1/4. So this happens there. Oops. That's already a px. It should be 1/4. So that's the individual graph for species 1. Now I got to draw the individual graph for species 2 before I can combine them and look at both species together. So the fitness of the x and y types depends upon the fraction of a and b types. Like my right example, the fitness of the mice depends upon the fraction of what kind of cats are out there. So let's see, what do we say our fitness of each type was there? We said the x types have fitness level of PA, so that's going to be intercept of 0 and slope of +1. We said the y types have fitness level of 3 minus 3 PA, intercept is 3, slope is -3. And when are they equal? We solved for that back in step 2. We said that the x types and y types were equally fit when PA was 3/4. So that's when those two lines cross over. So that's the graph for each individual species, but we're not done yet. Like I said, we also have to look at the species together to analyze the stability of the equilibria. So here's what that's going to look like. So we're going to draw a box here because we have two axes. I'll put px on this axis over here, and px can go from 0 to 1. And I also have PA that I'll put over here that also ranges from 0 to 1. So every coordinate in this box here corresponds to some fraction of A types and some fraction of X types. Now, we know there are going to be different regions in the box depending upon which type is more fit. So we know that the A types and B types are going to be equally fit when px is 1/4. So px being 1/4 is going to be somewhere around here. We also know that the x and y types are equally fit when PA is 3/4. Same as before, I'm going to draw a line corresponding to that. So 3/4 is around here. So for the equilibria, there we have monomorphisms where everybody's the same type, and we also have the polymorphism where there's a mixture of types. So the monomorphisms are all the corners here. This one's all A types, all X types. This one's all B types, all X types. All Y types, all B types. And all A types, all Y types. You got this one in the middle here was a mixture. So now you gotta look at the stability of each of those equilibria. So you gotta understand the dynamics of the system. This gets a little bit trickier compared to what we saw earlier. So we'll look at each one of these four regions. So we're going to combine these graphs together to figure out what's going on in the dynamics over here. So let's say that px is below 1/4, looking at this side of the box. When px is below 1/4, we go to this graph over here. That tells us that when px is between 0 and 1/4, then the B types are fitter. So in this region, the B types are fitter. That means that the number of A types is going to go down, so there's going to be downward pressure on PA. The B types will reproduce more, pass on their genes, live longer, and they're going to see the A types die out. So when px is less than 1/4, PA is going to be going down, so I draw a down arrow in these boxes over here. Let's look at the other side, these two. So here, px is greater than 1/4, but it's less than 1. That corresponds to this region on our first graph. So when px is high, what's going on? We say that when px is above 1/4, then the A types are fitter. When the A types are fitter, the A types will live longer and pass on their genes, and reproduce more. So the fraction of A types will increase when px is high. So P is in this axis, so P is going up. We draw up arrows in that case. Now we're not done yet. We found the dynamics for PA. We found when does PA go up and when does PA go down. We also defined the dynamics for PX. So let's start. Over here when PA is high. So when PA is above 3/4 and PA is getting close to 1, our graph over here is going to tell us what's happening. When PA is big, then the X types are more fit than the Y types. So high PA is going to mean that X types will live longer and reproduce, so PX is going to be increasing when PA is high. So PX is out here, that's going to start going up. Then I got to draw arrows going this way. So that shows that a high PA corresponds to X types being fitter. Now let's look at when PA is low. So PA is between 0 and 3/4. That means we're back here on this graph. So this part of the graph corresponds to these two regions. So if PA is small, then the Y types are now fitter. Because the Y types is way up here, fitness of the X types is down there, so the Y is going to be the ones who are reproducing, and the X types are the ones that are going to be dying off. So in that case, Y types are fitter, so the fraction of X types is going to be decreasing. So you'll see fewer X types and more Y types. If the fraction of X types is going down, then you got to draw arrows going the other way. So this shows that X will be falling in this region, and also over here, PX is going to be falling as well because of a low PA. So that's how you manage to combine these two individual graphs into a single combination graph. And with our arrows here, we now have the tools to analyze stability. So let's start with this one down here, where PA is 0 and PX is 0. So that's a monomorphism. We gotta see if it's stable or not. So to check stability, you gotta follow the arrows. So you gotta think about, if I had some small deviation from this equilibrium, if I went from here to out here, do I go back to the same equilibrium, or do I end up going somewhere else? Well, in this case, the arrows are pointing this way, so if I were to deviate in this direction, these arrows are going to push me right back to where I started. So if you combine those together, you're going to get some direction that's this way. So if I go back to where I started, that's stable. So you call it an evolutionary stable strategy, an ESS. So that's one of the equilibria. We gotta look at all the other equilibria as well. There's also this one over here where PA is 0 and PX is 1. So the same kind of thought experiment. If you leave that equilibrium by a little bit, if you go up over here, do the arrows push you back to where you started, or do the arrows take you somewhere else? Well, in this region, the arrows are pointing this way. So if I start moving in this direction, the arrows are going to take me further and further away. So that's not going to be stable. Next equilibrium to study. There's this point up here where both PA and PX are 1. Standard procedure, start from the equilibrium, change a little bit, and then do the arrows take you back where you started, or do the arrows push you in some other direction? So these arrows are going to point up and to the right, so if you combine them, they're going to point in this direction. That's going to push us back where we began. So that's going to be stable. That's another ESS. Evolutionary stable strategy. So another monomorphism is that what if we have PX being 0 and PA being 1. So we're up here. So if I start from that equilibrium and I move out a little bit, what happens? My arrows are going to push me down and to the right, so that's going to push me further and further away. So if I start here and move a little bit, I don't come back. That's going to be unstable. All right, we have one more equilibrium to look at. So there's also that polymorphism where you have a mixture of types. So what if PA is 3/4 and PX is 1/4? Analyzing that one's going to be a little bit more work, but nothing unmanageable. So I look at if I deviate a little bit, do I go back where I started, or do I get taken somewhere else? Now why this is a bit more complicated is because deviate a little bit could take me in any one of these four directions. So before I was looking at equilibrium out here, there's only one region I could go to. I'm still going to be in this rectangle here. Here, however, there's a multitude of possibilities, so I got to check each one. So if I were to go from this point up over here, the arrows are going to push me back. So these arrows are combined to push me in this direction. So I go back where I started. That looks all right. But what if I deviate a little bit in a different direction? If I were to go out here, for example, now do the arrows push me back where I started, or do they take me elsewhere? Well, in this case, the arrows are pushing me up and to the right. So I start going here, I'm going to be pushed further and further in that direction. So that's going to take me away from where I started. So that's going to be unstable. So how I know that, we got to make our definition of stability a bit more precise here. So it looked like I was stable when I went from this direction. I went this direction because I got pushed back where I started if I go there. However, it looked unstable I go in that direction because then I get pushed further and further away. So for equilibrium to be stable, it has to be stable in every direction. If it's unstable in at least one direction, then you call it unstable overall. So because I found one case where it was unstable, that's how I know this equilibrium is overall unstable. You could also check the other directions if you wanted to. However, once again, it suffices to find a single unstable direction. If I were to go from here down to this block, in this rectangle, then my arrows are going to push me in this direction. That pushes me back to where I started. So that direction looks stable. But again, I found one unstable direction, so that's how I know this overall can't be stable. Last possibility is that what if I deviate a little bit to go in this direction over here? Well, in that case, my arrows are going to be pointing this way. So that's going to pull me further and further away. As I was saying before my phone ran out of memory, if you go in this direction, it's also going to be unstable. The arrows are going to take you further and further away, so that's not stable. So someone once asked me about these other points, like these ones over here or over there. Those ones are always going to be unstable. That's because you can see these arrows here are going to be pointing in the same direction this side. So you deviate anywhere from that, you push further and further up with PA. Or if over here, you push further and further down if you deviate from this point. So you don't have to worry about those points. Look at the four corners and the one in the middle for your stability analysis. Now, one thing we like to do here is compare our evolutionary stability analysis with what does economic game theory tell us. So we established that there are two ESSs here. So let's find out what the Nash equilibrium would be with economic game theory. So let's go back to our original game. And I'll find a Nash equilibrium with the usual best response analysis. So if you're species 1 and your opponent is playing X, what is your best response? You want to play A and get 3. If your opponent is playing Y, your best response is to play B and get 1. If you're playing A, your opponent's best response is to play X. If you're playing B, opponent's best response is to play Y. So the Nash equilibria are going to be AX and BY. And there's also going to be a mixed strategy Nash equilibrium. Where you play A 3/4 of the time and X gets played 1/4 of the time. So the polymorphism is analogous to the mixed strategy Nash equilibria. So how does that match up with our stability analysis over here? Well, Px equals 0 means you never play X, it means you always play Y, and Pa equals 0 means you never play A, you always play B. So this one corresponds to By. And we said that one was stable. And this one here, AX, that's like playing A all the time, P equals 1, and playing X all the time, Px is 1. So that's this. And we said that one was also stable. Lastly, we have this mixed equilibrium over here, where you play A 3/4 of the time, and X gets played 1/4 of the time. So we said that one was unstable. So the same principle we had earlier still holds, and that principle was that every ESS, every evolutionary stable strategy, is a Nash equilibrium. So our two stable strategies were both Nash equilibria. However, not every Nash equilibrium is evolutionary stable. We have one Nash equilibrium that's unstable, so that shows that part of the principle as well. So that wraps up chapter 12. I just have one final note for you guys. So as I explained earlier, my scanner at home is very slow, so I've been uploading last year's notes rather than what I'm writing down over here up on my courses. So what I was doing with last year's notes is that in addition to the graphical analysis, I also did a mathematical analysis of stability. I dropped that this time because I realized the mathematical analysis is more complicated and it does the exact same thing. So just go the simple approach of doing the graphs like I did here and don't worry about the mathematical stability analysis you see in the notes I uploaded. So that's all for chapter 12. So come join us next time for our next episode, which will look at chapter 16, bidding strategy and auction design. In the meantime, stay safe out there.